Okay, in this class, I am going to talk about the identification of Raman active vibrations using group theory. In the last class, we discussed the identification of IR activity of vibrations using group theory. Okay, and here we are going to talk about the Raman active vibrations. And the requirement for a vibration to be a Raman active is that vibration should accompany a change of the polarizability. Polarizability. A change of the polarizability. Okay. So the vibration should accompany the change in the polarizability. What is the meaning of that? You suppose a molecule. Okay. A molecule is like this. Here is a molecule. These are the two nuclei. Okay. And surrounding this nuclei, there will be an electron cloud like this. An electron cloud like this. Okay. So this is the electron cloud of the molecule surrounding the nuclei. And you suppose that this electron cloud is symmetrically distributed around the two nuclei, so that the net dipole moment of this molecule is 0. Suppose that both of these are the same nuclei. Okay. But what will happen if you are bringing this molecule in an electric field? You are placing this molecule between two metal plates carrying the electric charge. Okay, so that you are applying an electric field into this molecule. So what will happen if you are doing this one? The electronic charge cloud here surrounding the two nuclei in the molecule will be repelled from the negative part of the field, and then it will be attracted towards the positive part of the field, right? So after some time you can see that it will take another orientation like this, or the electronic charge cloud will be distorted, and the electronic charge will be something like this one. So you suppose these are the this is a new state of the system. The two nuclei are there. You suppose that the position of the nuclei are fixed. Okay, so you can see that the electronic charge cloud will be more towards the positive end of the electric field. Okay, so it will be more towards the positive end, and the electronic charge cloud towards the negative side is reduced. What will happen if this type of a distortion happens in the electronic charge cloud around the molecule? Initially, when there was no applied field, this molecule was a non-polar molecule. But by applying an electric field, now there is a polarity set up inside the molecule, because the electronic charge cloud is no longer uniformly distributed around the two nuclei, but the electronic charge cloud is distorted. So because of this, there will be a dipole moment, right? There will be a dipole moment. So the dipole moment which is being originated by the induction, or by an electric field, by the influence of an electric field like this, it is called the induced dipole moment. Therefore, this molecule now at this state has an induced dipole moment. Dipole moment. Induced dipole moment. Let me call this induced dipole moment as mu I. Okay, and this mu I depends upon two factors. The factors are: one is the electric field strength, and another factor is how easy is it to distort this electronic charge cloud around the molecule. How easy is it to distort the electronic charge cloud, or how easy is it to pull the electronic charge cloud from the clutches of the nucleus? Okay, that is another factor. So easiness of distorting the electronic charge cloud, that is called the polarizability. Let me represent this as alpha. So the induced dipole moment mu I will be the product of polarizability alpha and the electric field strength E. It means that if the polarizability is very high, then the induced dipole moment will be very high. If the polarizability is very high, it means that it is very easy to distort this electronic charge cloud. If it is very easy to distort the electronic charge cloud, then the polarizability will be, then the dipole moment can be easily created, right? So mu I depends upon the polarizability, and also it depends upon the electric field strength, because it is the electric field strength which is causing the pulling, or which is pulling the electron density towards a certain side, right? So if the electric field strength is very high, it can pull the electron density or push the electron density with a better strength. So the induced dipole moment also depends upon the electric field strength. So induced dipole moment mu I is equal to alpha into E, where alpha is the polarizability and E is the electric field strength. So the induced dipole moment mu I, this induced dipole moment mu I, okay, this mu I has three mutually perpendicular components in x direction, y direction, and z directions. Okay, so the three mutually perpendicular components of mu I are mu I x, mu I y, and mu I z. These are the three mutually perpendicular components of the induced dipole moment. And the electric field E also has three mutually perpendicular components along the xy direction, xy and z direction. These are Ex, Ey, and Ez. Okay. So the induced dipole moment has three mutually perpendicular components, and the electric field also has three mutually perpendicular components. But don't think that this component is decided by Ex alone. That is not the case. The component of the electric field strength in the x direction is not only decided by, or not only determined by, or not only set up by the electric field component in the x direction, but it is also influenced by the electric field component in the y direction, and it is influenced by the electric field component in the z direction. Okay, so mu Ix depends upon Ex, Ey, and Ez. Like that, mu Iy depends upon not only on Ey but also on Ex and Ez. So it's the case with the mu Iz also. So if you are checking at the electric, if you are checking at the, or if you are looking at the component of the induced dipole moment in any direction, that component is determined by, or that component is set up by the electric field component in all directions. Do you have any doubt about that? I will explain why it is like that. I already said the induced dipole moment is due to the distortion of the electronic charge cloud in the molecule. The induced dipole moment mu I is due to the distortion of the electronic charge cloud in the molecule. And now I am going to make an analogy. Okay, I am going to take a balloon filled with water. Okay, so here is a balloon, and this balloon is filled with water. Okay, it is tied here, and water is inside in this balloon. There is water inside this balloon. Okay, it is filled with balloon, and this balloon is a highly flexible balloon. And what I am going to do is that I am going to look at this balloon from all directions. Let me look at this balloon from the x direction. Okay, from the x direction. This is the x direction. I can look at this balloon from the z direction. This is the z direction. And I can look at the balloon from the y direction as well. Okay, I have an impression of this balloon from all directions. Now what I am going to do is that I am going to press this balloon from the x direction. Okay, I am going to press this balloon from the x direction. So let me press this balloon from the x direction. After pressing the balloon from the x direction, what will happen? After pressing the balloon from the x direction, its shape will be distorted, right? So this is the x, y and z axis. This is x, this is z, and this is y. So after this balloon is being pressed from the x direction, its shape will change. The shape will change like this. Okay, this pressed from here. The shape will change like this. So now you can see that the balloon is not only distorted in the x direction. So obviously when you are viewing this balloon from the x direction, its shape will change. And you can also see that if you are viewing this from the z direction, then also the shape of the balloon is changed. If you are viewing it from the y direction, also the shape of the balloon is changed, right? So even if you pressed the balloon from the x direction, it changed its shape in all directions, right? The thickness of the balloon will be different in all directions. This is because the water has to adjust somewhere, right? When you are pressing the balloon, the water inside the balloon has to adjust some volume somewhere. So it will try to accommodate, it will this water will try to accommodate some volume in all directions, not only in the x direction. It will push the balloon, the boundary of the balloon, in all directions, z and y also. So is the case with the electronic charge cloud also. The electronic charge cloud can be viewed as a balloon full of water. Okay. So when an electric field is applied along the x direction, the electronic charge cloud will be distorted. So the effect of this distortion will be in all directions, not only in the x direction, but also in y and z directions. So if the shape of the electronic charge cloud is, and if it is changed in all directions, you can say that the polarizability is set up in all directions, or there is an induced dipole moment is set up in all directions, right? The induced dipole moment is set up in all directions because the induced dipole moment is due to the change in the shape of the electronic charge cloud. If it is changed in the x direction, of course there will be an induced dipole moment set up in the x direction. If it is changed in the y and z directions, of course there will be an induced dipole moment set up in those directions as well. But you applied the field only in the x direction. So even if you applied the field in the x direction, the induced dipole moment is set up in all directions. Or in other words, the induced dipole moment in any direction will be influenced by, or will be set up by, the electric field component in all directions. അല്ലേ? അപ്പൊ നിങ്ങൾ എക്സ് ഡയറക്ഷനിലാണ് ഇലക്ട്രിക് ഫീൽഡ് കമ്പോണന്റ് അപ്ലൈ ചെയ്തതെങ്കിലും ഇൻഡ്യൂസ്ഡ് ഡൈപോൾ മൊമെന്റ് സെറ്റപ്പ് ചെയ്തത് എല്ലാ ഡയറക്ഷനിലും സെറ്റപ്പ് ചെയ്തു. നമ്മൾ തിരിച്ചു പറയുകയാണെന്നുണ്ടെങ്കിൽ ഏതെങ്കിലും ഒരു ഡയറക്ഷനിലെ ഇൻഡ്യൂസ്ഡ് ഡൈപോൾ മൊമെന്റിനെ നിങ്ങൾ എടുക്കുകയാണെങ്കിൽ that induced dipole moment is not only set up by the electric field component in one direction or in that particular direction, but also it will be influenced by the electric field component in other directions. അതുകൊണ്ടാണ് ഇവിടുത്തെ ഇലക്ട്രിക് ഫീൽഡ് കമ്പോണന്റ് എക്സിലുള്ള ഇലക്ട്രിക് ഫീൽഡ് കമ്പോണന്റ് വൈയിലും ഇസഡിലും എക്സിലുമുള്ള ഇൻഡ്യൂസ്ഡ് ഡൈപോൾ മൊമെന്റിനെ ഇൻഫ്ലുവൻസ് ചെയ്തു, അല്ലേ? അപ്പൊ ഏതെങ്കിലും ഒരു ഡയറക്ഷനിലുള്ള ഇൻഡ്യൂസ്ഡ് ഡൈപോൾ മൊമെന്റ് എന്ന് പറയുന്നത് ആ ഡയറക്ഷനിൽ മാത്രമുള്ള ഇൻഡ്യൂസ്ഡ് ഇലക്ട്രിക് ഫീൽഡ് മൂലമല്ല. കാരണം ഇവിടെ ഇസഡ് ഡയറക്ഷനിൽ ക്രിയേറ്റ് ചെയ്യപ്പെട്ട ഇൻഡ്യൂസ്ഡ് ഡൈപോൾ മൊമെന്റ് എക്സ് മൂലമാണ് വന്നത്. വൈ ഡയറക്ഷനിൽ ക്രിയേറ്റ് ചെയ്യപ്പെട്ട ഇൻഡ്യൂസ്ഡ് ഡൈപോൾ മൊമെന്റ് വന്നത് ഇലക്ട്രിക് ഫീൽഡിന്റെ എക്സ് ഡയറക്ഷൻ മൂലമാണ്. അതുകൊണ്ട് ഏതെങ്കിലും ഒരു ഡയറക്ഷനിലെ ഇൻഡ്യൂസ്ഡ് ഡൈപോൾ മൊമെന്റ് അല്ലെങ്കിൽ ഏതെങ്കിലും ഒരു ഡയറക്ഷനിലെ ഇൻഡ്യൂസ്ഡ് ഡൈപോൾ മൊമെന്റിന്റെ കമ്പോണന്റ് that is set up by the electric field component in all directions. That is why I said mu Ix not only depends upon Ex but also depends upon Ey and Ez. Okay, so I hope now you understood what I said. So even if you apply the electric field along the x-axis, the induced dipole moment will be created in all directions, or polarizability in any direction. The polarizability in any direction, be very careful. The polarizability in any direction is brought by the electric field component in all directions, right? The polarizability in any direction is brought by the electric field component in all directions. So let me call the polarizability in the x direction as alpha x. This is the polarizability in the x direction. But this polarizability in the component of polarizability in the x direction, that is influenced by Ex, Ey and Ez. Okay. Since it is influenced by Ex, let me call this as alpha xx. That is the component of component of polarizability in x direction, but it is brought by the electric field component in the x direction. Okay, the electric field component in the x direction, brought by electric field component in the x direction. So alpha xs is the component of polarizability in the x direction, brought by the electric field component in the x direction. Like that, the component of polarizability in the x direction is also brought by the electric field in the y direction. So let me call this as alpha xy. So alpha xy is the component of polarizability in the x direction brought by the component of electric field in the y direction. And alpha x is the component of polarizability in the x direction brought by the electric field strength or electric field in the z direction. See, I have alpha xx, alpha xy and alpha xz. These are all components of polarizability in the x direction, but it is brought by different components of electric field Ex, Ey and Ez. So mu Ix, that is the component of the induced dipole moment in the x direction, mu Ix. Okay, it is decided by all these alpha x's, alpha xy and alpha xz. So you can write like mu Ix is equal to alpha x x Ex. That is the component of polarizability in the x direction brought by Ex multiplied by the electric field strength Ex in the x direction. Okay, Ex plus alpha xy Ey plus alpha xz Ez. Okay, because you already know what is the expression for the induced dipole moment. The expression for the induced dipole moment is, sorry, the expression for the induced dipole moment is, here it is here. Expression for the induced dipole moment mu I is equal to alpha multiplied by E. That is what I have written there. Okay, alpha multiplied by E, alpha multiplied by E. All these are alpha multiplied by E, but there are three terms. This is because the polarizability has three components brought by Ex, Ey and Ez. Okay, and like that I can write mu Iy, that is the component of dipole moment, induced dipole moment in the y direction. Okay, that is equal to alpha yx where alpha yx is the component of polarizability in the y direction brought by the electric field component Ex multiplied by Ex plus alpha yy Ey plus alpha yz Ez. And similarly, I can write mu I z, that is a component of induced dipole moment in the z direction. It is determined by alpha z x Ex plus alpha z y Ey plus alpha z Ez. Okay. So now you can see that the polarizability terms. What are the polarizability terms here? Alpha xx. Okay, this is a polarizability term. Here is another polarizability term, alpha xy, alpha xz, alpha yx, alpha xy, alpha yz, alpha yxz, zx, alpha xy, and alpha zz. 9 polarizability terms are there, right? 9 polarizability terms. But you have to consider that alpha x y is equal to alpha y x. Alpha y z is equal to alpha z y, and alpha x z is equal to alpha z x. Okay, so these equalities also exist. And similarly, let me denote alpha x x as alpha x square. Let me denote alpha y as alpha y square, and alpha z as alpha z square. Okay, so if we are taking these into considerations, how many components are there for the polarizability? The components of polarizability are alpha xy. Okay, I don't need to write alpha yx again because alpha xy is equal to alpha yx. Then I have alpha x, alpha yz, and then alpha yz, and then I have alpha xz. Okay, 3 from there, and then alpha x square, alpha y square, alpha z square. So how many components are there for the polarizability? 6 components are there for the polarizability. 6 components are there. So the polarizability has 6 components. Now I am going to consider the probability of transition P. Probability of transition P. That's just like we considered in the case of IR or infrared active vibrations. Here the probability of transition P will have 6 components because polarizability has 6 components, right? In Raman spectra, it is the polarizability which is the deciding factor. In the IR spectrum, it is the dipole moment which is a deciding factor, right? That was the dipole moment because in the case of IR active vibrations, there is a dipole moment change. In the case of Raman active vibration, there is a polarizability change. So in the case of IR active vibrations, we had 3 components. Okay, 3 components for the probability of transition because the dipole moment had 3 components. Here we have 6 components for the probability of transition because the polarizability has 6 components. 6 components. 6 components for the polarizability. Okay, so corresponding to these 6 components of polarizability, we have to write the equation for the probability of transition P. Okay, so let me write this equation for the probability of transition P. So the probability of transition P that is proportional to minus infinity to plus infinity. Okay, you already know psi I p cap psi f d tau. This is equation. We have already seen this equation in the case of IR spectrum. And what is the p cap here? This is the operator, the transition moment operator. And in the case of IR, we took p cap as the dipole moment, right? But here we have to take the p cap as the polarizability. And the polarizability has 6 components. These are the binary products like xy, xz, yz, x square, y square, z square, right? So let me call this binary product as AB. So AB can be the binary product of x and or y, right? Like AB can be xy, yz, xz, x square, y square, z square. So the AB represents all these binary products. So the probability of transition PAB, it is proportional to minus infinity to plus infinity psi I AB, that is operator here, okay, AB psi f d tau, where AB is the component of polarizability, okay. And now I am going to find out I'm going to find out PAB. PAB means I have to give xy, xz, yz, x square, y square, z square in place of AB, and I have to evaluate this integral. Evaluate means I don't need to get the absolute value of this integral, because I am only interested whether this integral is 0 or non-zero. If the integral is 0, if it is a 0, then it means that there is no transition probability. There is no spectral transition, or there is no Raman active vibrational transition. Okay? And if the integral is a non-zero, then it means that yes, there is a transition. Yes, there is a transition corresponding to that. So in this case, it is a Raman active. Raman active. If it is Raman inactive, sorry, Raman inactive. If there is no transition, it means that it is Raman inactive. Let me write better. So it is Raman inactive in this case. Raman inactive. If it is 0, it is Raman inactive. Okay, and if it is not 0, then it is a Raman active. So in order to see whether a particular vibration is Raman active or Raman inactive, we have to calculate this transition moment integral corresponding to that vibration. Here psi I is the state of the system, the ground vibrational state, ground vibrational level, the state of the system, the state function representing the ground vibrational state, state function representing or corresponding to the ground vibrational level, the ground vibrational level. And psi f, it is the state function corresponding to the excited vibrational level. Okay, this means during a vibration, the molecule will make a transition from the ground vibrational level to an excited vibrational level. I have already explained this well in the case of the IR. Okay, and that is why I am not explaining too much here. So this psi represents the state function corresponding to the ground vibrational level. Psi f is the state function corresponding to the excited vibrational level. And AB represents the operator here. Okay, and it corresponds to x, y, x, z, etc. Okay, here. And we know that we have to evaluate whether this integral is 0 or not 0. Normally, we can depend upon a computer to evaluate this integral. If you have the state function for the final and initial states, and if you have the operator like this, then you can depend on a computer to solve this integral, right? And you can see whether what is the value, whether it is 0 or whether it is a non-zero value. Okay. Depending on that, you can predict whether it is Raman inactive or Raman active. But you don't need to depend upon a computer to say that. You can depend on the group theory. That is a shortcut. Without using a computer, by looking at the character table, you can say whether this integral is going to be 0 or non-zero. Though I am going to explain this how it is possible. Okay. So if you have already gone through my previous lecture for the IR spectroscopy, then it will be very easy for you, okay, to follow this lecture. And now I am going to evaluate this integral in many cases. So we don't need all the integrals corresponding to x, y, y, z, x, z, etc. to be non-zero for the Raman activity. Any of the components of the probability of transition can be non-zero. Then it will be Raman active, just like we considered in the case of the IR. So let me take, for example, the example of water molecule. Okay, so I am going to take the example of water molecule. I am going to take this example because for this water molecule we have already identified the symmetry species corresponding to the vibrations. We saw that in the case of water molecule, there are three fundamental modes of vibrations. And these vibrations are symmetric stretching, symmetric bending, and anti-symmetric stretching. Okay, symmetric stretching, symmetric stretching, then symmetric bending, and anti-symmetric stretching. Okay, these are the normal modes of vibrations. And we have assigned the symmetry of the normal modes of vibrations. We have seen that the symmetric stretching corresponds to A1 symmetry. Symmetric bending also corresponds to A1 symmetry. And the anti-symmetry stretching corresponds to the B2 symmetry. Okay, we have already done this. If you have not seen my in my class regarding this, I recommend you to go to that class first. Okay, that is very essential for understanding this lecture. So the symmetric stretching, symmetric bending, and anti-symmetric stretching can be assigned the symmetry species A1, and B2 respectively. Okay, so the molecule executing the symmetric stretching will be in the ground vibrational state, means V is equal to 0 state. And the molecule with the symmetric bending and asymmetric stretching can also be in the ground vibration state. So how can we get the symmetry species corresponding to the ground vibration state? We just need to take A1 raised to 0. Here I have taken A1 raised to 0 because V is equal to 0. That is the symmetry species corresponding to the ground vibration state. That is nothing but A1. And here also I have to take A1 raised to 0 because this normal mode is in the 0 vibrational level. V is equal to 0 vibration level. So this is also equal to A1. And here also in the anti-symmetric stretching mode, that the normal mode corresponds to B2. And when the molecule is executing the anti-symmetric stretching at the ground vibrational level, then the symmetry corresponding to that is B2 raised to 0. Okay, that is equal to A1. B2 raised to 0 is also A1. I have already explained this in the case of IR spectroscopy. Why B2 raised to 0 is equal to A1? B2 raised to 0 means the characters in the B2 representation rise to 0. Any number rise to 0 is equal to 1. Then you will get 1, 1, 1, 1. Okay, all 1. All 1 corresponds to A1 symmetry. That is why B2 raised to 0 is equal to A1. So we can see that all the vibrational modes in the ground state will be of A1 symmetry. And now this vibrational level, now this molecule in the ground vibrational level can absorb radiation and make a transition to the next vibrational level. Okay, the next vibrational level is equal to V is equal to 1 stage. So in the next vibration level, this is an excited vibration level. Okay, excited vibration level. Its symmetry will be A1 raised to 1. A1 is the symmetry of the normal mode here, and A1 raised to 1 is equal to A1 itself. It means that the molecule executing the symmetric stretching, when it makes a transition, the symmetry of the transition is A1 to A1. Okay, and here also when it is making a transition to the V is equal to 1 state, its symmetry will be A1 raised to 1, that is equal to A1. So this molecule, when it is executing the symmetric bending and when making a transition from the ground vibration level to the next higher vibration level, the symmetry of the transition is A1 to A1. And what about this one, anti-symmetric stretching? This is V is equal to 1 state. Therefore, in the excited level, its symmetry is B2 raised to 1. And that is equal to B2. Any number raised to 1 is the same number, right? So all the characters will remain the same. So here you have to note that when this transition takes place, it is A1 to B2 transition. A1 to B2 transition. So in every structure, every vibrational mode, you will see a particular type of transition. This is in the case of symmetric stretching, it is A1 to A1 transition. In the case of symmetric bending, it is also A1 to A1 transition. So in these two cases, this is of same symmetry, A1 to A1 transition, A1 to A1 transition. Which are the A1 to A1 transition? Symmetric stretching and symmetric bending. They have the A1 to A1 transition. But in the case of asymmetric stretching, we have A1 to B2 transition. B2 transition. It means that psi 1, that is the initial state in this case, psi 1 or psi I, initial state in this case, that belongs to the A1 symmetry. And the final state psi f in this case also belong to A1 symmetry. But in this case, the initial state psi I belongs to A1 symmetry. But the final state psi f that belongs to B2 symmetry. Okay. So psi I to psi f in this case is A1 to A1. In these two cases is A1 to A1, and psi I to psi f in these two cases is A1 to B2. Okay, you remember what are psi I and psi f. In the next, just a few minutes ago, I explained what are psi I and psi f. Okay? Right, you can see here. Psi I is the state function, the ground vibration state. Psi I is the state function, the excited vibration level. Okay, now we know the symmetry of the ground vibration level and the excited vibrational level. Okay, so now we know the symmetry of psi I and psi f. And if we know the symmetry of the operator also, we can determine whether this integral is going to be 0 or non-zero. So I am going to evaluate this integral for the water molecule. Okay. And let me do this. Let me first take x square. Okay. That is the component of the probability of transition corresponding to x square. Component of the probability of transition corresponding to x square. Okay. So that is px square. Px square. So in place of PAB, I write px square. Px square is proportional to minus infinity, integral minus infinity to plus infinity, psi I, then x square, psi f d tau. And what is the result of this integration? Whether it is non-zero, whether it is 0 or non-zero, we can find it out by analyzing the symmetry. Psi I in all cases belong to A1 symmetry. And what about the symmetry of x square? For that, we have to look into the character table. So in the character table of the C2V, you can see that x square, here is x square. X square belong to A1 symmetry, right? X square belong to A1 symmetry. So x square, y square and z square, all of them belong to A1 symmetry. So I can assign the symmetry of x square as A1. Okay, symmetry of x square as A1. So x square transforms as A1. So A1. And what about the symmetry of psi f? In the case of symmetric stretching and symmetric bending, it is A1 itself. So let me first consider symmetric stretching and symmetric bending. Okay, let me write it here. Symmetric stretching and bending. That is what I am considering. Symmetric stretching and bending. These are the two modes I am considering at this moment. Symmetric stretching and symmetric bending. So the final state is of A1 symmetry. So A1, 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 the direct product of A1, 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 that is equal to A1. Okay. It means it is totally symmetric. Totally symmetric. If the direct product is totally symmetric, the integrals corresponding to that will be non-zero. So this one is not equal to 0. Px square is not equal to 0. So it means that the vibration is Raman active. Like that, you can show that py square is also not equal to 0, because py square also, the y square also is also of A1 symmetry. We already saw that, right? Py square is not equal to 0 and pz square is also not equal to 0. Okay. And if any of these components is non-zero, Now you can find out x, y, x, z, and y, z also. I'm not going to that too much of that because it is not necessary. If any of these components is non-zero, then the vibration will be Raman active. Okay. So the symmetric stretching and the symmetric bending, these vibrations are Raman active. So symmetric stretching, symmetric stretching and bending vibrations are Raman active or Raman active. Raman active. Raman active. That is what we can understand from here. So we didn't evaluate any integral using a computer or by using any sophisticated method. We just looked at the symmetry and then we saw that this vibration, symmetric stretching and symmetric bending are Raman active. Okay. So here we have seen that whatever may be psi f in this case is A1, right? Psi f belong to A1 symmetry. A1 symmetry. And psi f is A1 symmetry. It is because the normal mode itself has the A1 symmetry. Normal mode itself has the A1 symmetry. See, this is the A1 symmetry. Symmetric stretching and symmetric bending has A1 symmetry. A1 symmetry. The normal modes belong to A1 symmetry. So why v is equal to 1 state actually is this rise to the power 1. So it will be this one itself. So psi f and the normal modes, the psi f will have the same symmetry as we calculate it for the normal modes of vibrations. Okay. So if any of the binary products are coming in the character table in the same symmetry species corresponding to the normal mode of vibration like this. See, the normal mode of vibration for the symmetric stretching and symmetric bending is A1. If any of the binary products are coming in the same line in the character table, then it will be a Raman active vibration. Here we have x square, y square and z square. These are coming in the same representation. It is same representation of A1. So it will be Raman active. Any vibration with the A1 symmetry will be Raman active. Okay, that is what we have proven here. So that is symmetric stretching and the symmetric bending are Raman active. Now I am going to evaluate anti-symmetric stretching. Anti-symmetric stretching. Anti-symmetric stretching. Anti-symmetric stretching. And for anti-symmetric stretching, you know that psi I is of A1 symmetry. Psi f is of B2 symmetry. We already saw that here, right? Psi f is of B2 symmetry. And now we have to evaluate the integrals. So let me look at the character table itself. Before evaluating all the 6 integrals, let me look at the character table. This is B2 symmetry. In the B2 symmetry, you can see a binary product that is YZ. Okay, that is YZ. So let me evaluate the integral PYZ. That's all. PYZ. So PYZ is proportional to integral minus infinity to plus infinity psi I YZ psi f d tau. And whether this integral is 0 or non-zero, that depends upon the symmetry of these 3 terms. Psi I has A1 symmetry. YZ has B2 symmetry, we have already seen. And psi f also has B2 symmetry. So what about B2, B2? B2, B2 is equal to A1. Therefore, we can write it like A1, 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 A1. So that is equal to A1. Means this direct product is totally symmetric. Totally symmetric. If this direct product is totally symmetric, the integral corresponding to that will be non-zero. So Pyz is not equal to 0. If Pyz is not equal to 0, if any of the components is not equal to 0, then that vibration will be Raman active. Therefore, anti-symmetric stretching vibration. Stretching vibration is a Raman active. It is a Raman active. Raman active. Raman active. So we have seen that all the vibrations in the water molecule are Raman active. Symmetric stretching, symmetric bending are Raman active, and anti-symmetric stretching is also a Raman active. So how can we decide whether a particular vibration is Raman active or not? You look at the symmetry of the normal modes of vibrations. Okay, symmetry of the normal modes of vibrations. Here we have a 2A1 plus B2. These are the symmetry of the normal modes of vibration in the water molecule. There are two A1 symmetry modes and there is a B2 symmetry mode. The A1 symmetry modes are symmetric stretching and symmetric bending. And you look at the A1 symmetry in the character table, A1 representation in the character table, and check whether there is any binary product appearing in that line. Yes, it is there. If it is the case, then the vibrations belonging to this A1 symmetry will be Raman active. So symmetric stretching and symmetric bending are Raman active. And the third vibration is anti-symmetric stretching that belongs to the B2 symmetry. And now you look at the character table and corresponding to the B2 there is a binary product that is Y is such. Therefore, since there is a binary product Y is such in the B2 line, then the mode represented by the B2 symmetry will be Raman active. That is, anti-symmetric stretching will be Raman active. So what we can conclude from here? So we can conclude that a fundamental transition will be Raman active if the normal mode belongs to the same representation as one or more of the binary products of the Cartesian coordinates. Let me write it here. A fundamental transition will be a fundamental transition will be Raman active if the normal mode belongs to the same representation. If the normal mode belongs to the same representation as one or more of the binary products of the Cartesian coordinates Okay, so this is what we can conclude. A fundamental transition will be Raman active if the normal mode belongs to the same representation as one or more of the binary products of the Cartesian coordinates. So I hope you understood how to determine whether a particular vibrational mode is Raman active or not. We have discussed this in detail. We have seen that group theory is a shortcut in order to avoid the lengthy, laborious calculations as provided by the quantum mechanics. Okay, so looking at the symmetry, we can jump to the conclusion whether a particular vibration is going to be Raman active or not, just like we did in the case of IR. I hope you understood this one. You followed this lecture. If you have any doubt, please don't hesitate to ask me. And thank you for watching and stay tuned.